Welcome everybody to another session of Lógicos in Quarentena. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to introduce Professor Hugo Mariano, who kindly accepted our invitation to give this talk. Hugo, thank you very much.
Thank you, Bruno, and thank you all the organizers by the invitation. It's really a pleasure to be here in Lógicos na Quarentena. And I will talk about this kind of funny subject, funny title, an algebraic framework to a theory of sets based on surreal numbers. So we need some explanation on the title, but it's a nice description of the work. Well, surreal numbers is a certain class of numbers that expands on one hand the ordinal numbers and the other hand the real numbers. This algebraic framework means some kind of categorical idea of to do to perform the constructions. And this name based on it's a kind of analogy between that occurs with the class of all sets and the class of the ordinal numbers. That's a kind of rank function. So this is the main idea here. It's a work I have developed with Dimi Rocha Rangel. This abstract is more or less than the same that was sent by Bruno to everyone. This means almost the same thing. I just have to say to you. And this is the diagram. So in the left side is the class of all sets and the class of ordinal numbers. This is the rank function and the inclusion of ordinals in the sets. And here in the bottom is this kind of inclusion of all ordinals in the class of surreal numbers that Conway, the guy that invented or defined the surreal numbers, called numbers. So this is kind of short version of numbers. And what we intend to do is to define another class of the same kind of the class of surreal numbers that's ranked on surreal numbers in a certain sense, and that includes the class or encodes the class of all sets. So this is the main idea, the main goal. And this is the structure of the talk. We will talk a bit of surreal numbers, then this algebraic framework called the algebras, as surreal algebras, it's short for surreal algebras. And there is another topic called ZF algebra, ZF for ZF set theory. This ZF algebra was defined in the 90s by two categorists, categorical and logicians, both. And there's a relation between ZF algebras and surreal algebras. And by this interaction allows us to define a kind of set theory in this kind of free surreal algebra that I put the name of SA for surreal and acyclic. And we finish with some remarks. Please interrupt me anytime if you need, if you want. Okay. So what are the surreal numbers? The notion of surreal numbers was done by John Conway in the 70s. And it's a class, a proper class that is linear ordered, but not well ordered. And this can be performed, can be defined with a background set theory like NBG or something stronger than that. And this is normally done by recursion on the class of all ordinal numbers. These surreal numbers, as I have said previously, is also a kind of expanded real numbers. So this is the name is not for Salvador Dali numbers, but by kind of expansion of the real numbers in the sense that they are a kind of universal real closed field. Let's go away. So the surreal numbers was created by Conway in the 70s. This is the book that where he defined this subject. And a few years later, Knut, from the guy that invented the LaTeX, published a book that's a kind of dialogue between two students that they, in the dialogue, they construct and explore the properties of the surreal numbers. It's a very interesting book. There's a previous pre-history of surreal numbers, given, for instance, on some papers like this Norman Allen paper on the existence of real closed fields that are eta alpha sets of power aleph alpha. So they define kind of class of very saturated fields that are ordered fields, in fact, real closed fields. And later, few years later, or a few decades later, to be more precise, Norman Allen realized that this, the surreal numbers are a kind of limit of this this class of fields, an ordinal limit on the class of ordinal. What is a surreal number according Conway approach? Conway just said that surreal numbers is a pair of sets of surreal numbers. To be a bit more precise, it's an equivalence class of pairs of sets of surreal numbers previously defined. So this is the notation for the class. So it's the L and R are the left and the right side of the representation. And every member of L is strictly less than every member of R. This is done by simultaneous induction or recursion numbers and in order. So given two sets of surreal numbers, satisfying this relation, meaning that every member of on the left side is less than every member of the right side. We can make a Conway cut, that is a kind of generalization of Dedekind cut. This is the standard notation in the books for a typical member of L or R. So, and a pre-order is defined in this setting in the following way. So x is less than y, if there is no right member of y that is less than x, and there is no left member of x that is greater than y. So this define a pre-order. This means a relation that is reflexive and transitive, and thus this define an equivalence relation in standard way. And let's do some example of numbers, of surreal numbers.
Hugo, pergunto, uma dúvida. Sorry, I have a doubt.
Okay.
Which are the initial surreal numbers? From which base you start to build the numbers?
Sorry, can you repeat, please?
Which are the initial?
It's just the empty set.
Okay.
You begin with the empty set on the left, on the right. It's possible to do that because every member on the empty set is less than every member of the empty set. So this defines a cut. So this is the initial step. Okay. Okay.
Okay. Thank you.
Okay. Can I go further?
Yes, please.
So let's see. Okay. Full screen. Everyone is seeing the screen.
Yes, you can see it.
Okay. So 0 is the class of the cut given by empty and the empty, and 1 is the number given by the set of number on the left given by the singleton on 0, and on the right by the empty set, and -1 is the kind of symmetrical construction. This suggests the opposite construction in this work, in fact. So if X is represented by Conway cut L and R, then -X is represented this way by reversing. It's a kind of inductive definition. And inductively, you can define also addition this way. So this we have to check that every member in the left side is less than every member of strictly less than every member of the right side here to do that. And multiplication expression a bit more complicated, but works. And in fact, this define a field, a proper class field. Okay. And there are many alternative constructions of the surreal numbers, the class of surreal numbers, and the structure of, let's say, field structure. But it's a much more easy to understand than the Conway original construction. And just put some short lists on these constructions. And moreover, not only there are many alternative constructions, as there are full axiomatization of this, the notion of the surreal numbers, and surreal numbers still are being studied by many people, including some people interested in analysis and in model theory. So, very interesting structure. So, just to make a list of the other constructions, all of them can be formalized in von Neumann-Bernoulli's Guido theory, class theory. There's the construction.
Hugo?
Yes.
There is a question by Juan. Is there an axiomatic approach to surreal numbers?
Sorry, my microphone is kind of. Please talk a bit.
I'm asking if there is any axiomatic approach to surreal numbers.
There is any
axiomatic?
Yes. I will show you in a few seconds. Okay.
Oh, okay. Thanks.
So there's this conic cuts, and this I do not do many details on these other constructions. There's a more clear construction given by Conway's games, and there's a intermediary notion between conic cuts and dedicated cuts called questadutari cuts. Questadutari is I don't know, Spanish or Colombian. And there's a very nice description given by signs, sequence of signs. I will show you in a few seconds. And this is done by Gonshaw in the maybe 80s. So the first three constructions are cumulative construction, and the sequences of signs are more direct construction. So let's see what's the sign sequence. This is just a function from with a domain an ordinal, and the range is the set with two elements that I have marked with a plus and minus. And you can define a kind of variation of lexicographical order here, denoting x is less than y, if only if x of alpha is less than y of alpha, where alpha is the least ordinal that x and y are different. So since the domains can be of the functions can be different, can be different ordinals, this difference can be done by because the domain are not equal. So there's a convention to deal with this, given that if beta is not in the domain of x, we define x of beta as 0 or empty. And the second convention that is minus is less than 0, then and 0 is less than plus. So with these two conventions, this is kind of variation of lexicographical order, and this corresponds to the order in the Conway construction of the surreal numbers. So, as asked, here is the kind of axiomatic, not first order axiomatic, of course, but since there is no hope to do that, there is no first order axiomatization of the class of the set of the real numbers, of the order field of real numbers. So we have to put some second order information here. This is done by a certain function from this class F to the class of all ordinals. B is the letter chosen because the people call this function as birthday function. When some surreal number is born at ordinal stage. So this is a birthday function. So the structure is like this: class, binary relation, and function from the class F to the ordinals. And the class is strictly linear order class. The birthday function is surjective. And there's two more technical conditions that are very interesting, and they do the job. So given Conway cut, let's recall, this means just that every member of the L is less than every member of R. So given any Conway cuts satisfying this property, if the birthday of every member of L is and every member of R is less than alpha, then there is a unique member of the class F, such that B of X, that's an ordinal, is minimal to this property. This means that X satisfies this property, and every member that satisfies this property has birthday greater or equal than the birthday of X. By this uniqueness, we denote this privileged member as by this notation, like in Conway description. So sorry, I have to replace this by L and R. So it's not F and G, of course. Here again, same problem. So the last property is given a Conway cut, satisfying the same limitation by alpha in his birthday. Then this special element is the class of this Conway
Hugo?
cut. Yes.
There is a question by Stephen Lamp. Should this be
Can you repeat?
Okay, it was answered already by you.
Okay. Is in the chat. The question.
Yeah, but you have just answered it in the following of your talk.
Let's see. Okay. Yes. That's it. Okay. It's L and R. There's a typo. I'm sorry. Two typos, in fact, in the same slide. Okay. Opa. Some funny things happen with everyone.
We can see it.
But my screen is freezing. You can see me, or you can see
we can see the presentation.
Okay. So just my computer. Okay, let's see. Okay. Now, so there's some problem with the full screen. Okay.
If you have problems with the full screen, you can give the talk not using full screen mode, just passing the slides in the standard window.
Okay. You seeing that?
Yes, maybe if you just close the tabs. Google, do lado dos marcadores tem um X, clica nele para fechar, depois clica na setinha do lado dessa barra da direita, só para ficar maior e as pessoas poderem ver melhor.
Ok. Vamos ver. Assim.
E nessa barra que tem uma setinha mais à esquerda. Mais à esquerda. Não, mais à esquerda. Não tanto. Nessa barra que tem exportar PDF, editar PDF, tem uma barra cinza logo à esquerda dela, que tem uma setinha apontando para a direita.
Não estou vendo.
É do lado direito da tela. Não tem essa barra que tem exportar PDF, editar PDF?
Ah, sim, sim.
Aí tem logo à esquerda dela, tem uma setinha apontando para a direita, nessa barra cinza vertical. À esquerda dela.
Ah, tá. Ah, ok. Pronto, é isso.
Pronto.
Obrigado.
Agora dá para ver bem.
Sorry about that. Okay. Can we go? Okay. So, what does it mean, lexometrization? Just this theorem of given by Allen. If you have two classes and data, in fact, satisfying these properties, it's called complete class of surreal numbers, just a name. So there is a unique isomorphism, structural isomorphism between these two classes. So this means that it preserves the binary relation, commutes with the birthday functions, corresponding birthday functions. So this is a uniqueness result. Okay. How we can see the ordinals inside the surreal numbers. We can do perform a recursion this way, given ordinal alpha. So the range of the set J alpha means the set of J beta for beta less than alpha. We can consider this as a left side of where the right side is empty set. So we define recursively this function, the kind of inclusion function, in fact. And this inclusion are preserves, in some sense, the ordinal arithmetic, in the sense that not the usual ordinal arithmetic, not that the sum and product usual sum of product of ordinals is not commutative, but they are associative. But there is another definition of called Hessenberg or natural operations on the ordinals that are in fact commutative and associative. This can be done using the Cantor-normal form of an ordinal and define some operations in a basis, where a basis is not 10 to the number, but omega to the ordinal number. Okay, but it's possible to do that, and in fact, this monomorphism is preserves this order and this same ring structure. Means preserves 0, 1, plus and multiplication. And is a retraction, is a section of the birthday function. So there's an inclusion of the ordinals in the surreal numbers, and there's a retraction that given by the birthday function that is surjective. Okay. So we go to the technical. So the technical definition that we have introduced is the notion of the surreal algebra, or just sur algebra, and given a class that may be a set or a proper class, we endow with a binary relation and a distinguished member, and a function from the class or set of Conway cuts of X associated to this binary relation. This T is a kind of term function given a pair of sets that's a Conway cut, determines or choose a single member of X, satisfying some actions that I briefly read with you. So recall that a Conway cut is a small Conway cut is a pair of sets, not classes, even if X is a class, proper class. A and B, such every member of A is less than every member of X. The name less than is strictly less than is not fully correct, but because we only assume that this binary relation is acyclic. This means in particular that is a reflexive relation, but this means more. That's there's no finite cycle of relations, ending beginning with some member and ending by this same member. I forget to add another function, minus, that goes from X to X, and this function minus is an involution given by this axiom. This distinguished element is a fixed point of this involution. This involution inverts the order relation, or this binary relation by this axiom. This term is between every member. The term function applied to A and B, to the Conway cut A, B, is greater than every member of A and smaller than every member of B. And this term is also can you see the last line or no?
Yes, not anymore.
Ah, okay. I don't know what is. Okay, no. And this distinguished member is the value of the Conway set, the trivial, the empty Conway cut given by empty set on both sides. But there's a kind of redundancy here. For instance, S3 is not can be derived from the others, and the distinguished member can be omitted by just by this using S7 as a definition, but not so important. So the surreal numbers are a natural example of this abstract definition. But the term is just the term function. The term associated to a Conway cut is given by this the class of equivalence associated to this Conway cut. And in fact, this term function is surjective for the sur algebra of surreal numbers. And other examples that can be defined recursively in this way. For each ordinal alpha, we define this by recursion this way. So S alpha, SA to the alpha are called the old numbers. These are Conway or Allen definition, old numbers, made numbers, and this part are called the new numbers. So one part we have to accumulate this alpha, S alpha, S8 to the alpha is a accumulation of the previous defined numbers. And we add some new information by the new members. The new members are pairs, pairs of sets that have occurred before, that are old members, and the relation between them are already defining this. So the relation also is done by accumulation and adding some new information. So the pair A-B is greater than every member of A and smaller than every member of B. In relation, add the more pairs we have to add. And the surreal acyclic algebra, SA, is just accumulation of these constructions that are sets in every ordinal level. So these are what we just have to just said to you. The SA to the alpha is the accumulation of the previously defined members, and we can show that there is a Conway cuts of SA are the same class of the Conway of the class of SA, and in fact this defines in a very natural way a surreal algebra that we will show that is a universal surreal algebra, and with some modification we can construct a surreal algebra that are transitive by almost the same thing, but with the relation that we add. Not only we add new order pairs like this, but we have to add the transitive closure of this relation, the previous relation. So this, if the less than to the alpha is acyclic, then in fact we can show that it's acyclic, in fact reflexive and transitive. Oh, and there's a analogous property. This is not the same class that the previous example, but it's almost there, because this relation is not the same the previous defined relation. Okay, so the class is cannot be the same previous defined. So a few remarks. It can kind of represent the surreal numbers inside this transitive, more free transitive surreal algebra. But this representation is do not preserve all the structure. There is a kind of no-go theorem that will not present the details, but you can represent part of this information, like in the same sense that ordinals cannot are included in the class of all sets, but not all the structure of the ordinals is represented in is preserved by this inclusion of the ordinals in the class of all sets. This is analogous. And in fact, every Sur algebra is a proper class, because even in any set, S for set, this small s is for set and also for small. So given any small part of the S in set subset, we can perform this this term, because this is a Conway cut, and because the relation is not reflexive, but particular, since this is acyclic, this cannot be reflexive. So this term cannot be a member of X in for any X that we set X that we choose, and the same way for the other side. So that's there's always a member that do not belongs to any subset of the class of the class S. So S is not a set; it's a proper class. Okay. This suggests that we have some kind of technical issues to do with this. We can do some constructions, but you have to take some care to define these properly. Okay? Since we are dealing with proper classes. The object, we can construct a very large category where the objects are surreal algebras. To be more precise, we can do as Grothendieck have done when we have a large information like category of all large category. We cannot do that in von Neumann-Bernoulli's Gödel class theory, but we can do a representation of this idea by the device of Grothendieck universe, that is encoding of the NBG theory in ZFC theory plus large cardinals. Okay, so this is implicit here. So we can do this category with some care, some theoretical care. So these objects are the surreal algebras, and the arrows are functions that preserve all the structure that are presented here. The binary relation, the distinguished member, the function minus, and this term function that goes from the Conway cuts to the surreal algebra. In fact, the Conway cut construction defines, in fact, a functor from this category to itself. It's an end functor, and the term function provides a natural transformation. The family of term functions provides a natural transformation between these two functors. So very easy, in fact, straightforward to define and prove this claim. And we depart from transitive surreal algebra, or linear, or strictly linear surreal algebra, and this Conway construction is also transitive or respective, almost linear, pre-linear. Something that we have to have some care with the pre-order. That's not antisymmetric order. Just a remark. To perform constructions, we have to depart from partial information. For instance, recall that by the cumulative constructions given by SA or ST, or even by surreal numbers construction, we depart from the empty. Okay, so in fact there is the empty surreal algebra, or the initial surreal algebra, that has only one member. That's the order pair given by empty. Partial surreal algebra, because that surreal algebra is a proper class, so we cannot depart from a small set size surreal algebra to perform constructions, because we will have from the beginning proper class. So partial surreal algebra is a very natural idea. Yes. And what is this? It's almost the same thing as surreal algebra, but we impose that the term function is not globally defined on all Conway cuts, but only in a certain subclass or subset of Conway cuts that stable on the having the initial pair, and that's stable also by minus function. So it's a very natural idea. We have many examples of partial surreal algebras. For instance, many mathematical examples, simple, in fact. Even any linear order group, abelian or not, and we can select a member of this group and consider an interval. This I don't care if A is positive or negative to define this. Just general notation. And from this interval, we can construct at least two different partial surreal algebras, where the distinguished member is the neutral element of G, and minus is the minus of the group structure, and the subset of Conway cuts may be this, the Conway cuts given by, let's say, a principal cut given by a member X, taking every member on the left of the X or every member of the right of X. And the term function is the more very natural definition. Let's choose the unique X between them, because this total relation. But there's another definition, alternative definition, that gives other structure of partial algebra here, but it's not so interesting. Now we can perform also the construction of a category of partial surreal algebras. Partial surreal algebras includes the surreal algebra, so we have to change to NBG to ZFC, but plus the Grothendieck universe to construct, in fact, these categories. And the morphisms are very natural. We have to preserve the let's say, first order structure and the partial second order structure given by pairs, for the pairs in the domain of the term relation that are not all the pairs. And we impose that they are preserved. They are, in fact, the image is in the domain of the T prime, and this equality holds. And but there's some technical definition that's called a full morpheme, but we don't need this here. We skip. And we can do this relative cut construction the very same way that we defined previously. And this cut construction is defined as a functor, and the term, the family of the term functions defines a natural transformation between the identity functor, between this cut construction and the identity functor of the category of partial subalgebras. This category of partial subalgebras has an initial object, is the partial subalgebra with only one member, and very standard way to define the domain of the term function, just a pair of empty sets, and has a product that is defined, non-empty products that is defined by component-wise, and it's a categorical product, and we have the notion of substructure and partial substructure of a partial subalgebra. But what is the main construction? This direct limit, this kind of gluing construction that can be performed in the category of the partial subalgebras, with some technical limitations or constraints, because we have not only a first order structure, but also information that is higher order, the term function. Yes. So we depart from a directed order class, omega directed order class, upper order directed, where in the diagram to this directed partially ordered set class, with the partial subalgebra that we impose that they are small, so the images are all small partial algebras or sets, and we have other limitations that if one of them is impossible, one possibility is to impose that the transition morphemes are injective, or we can impose more conditions on this directed class that is not only omega directed, but infinitely or set size directed ordered class, like the ordinals. So given any set of ordinals, there is an ordinal that is greater than every member in the set. This is the idea here. And if A or and B or A or C, we can define in this, more or less in this standard construction, colimit, and with these constraints, we can show that in fact is a partial subalgebra and is the colimit in this category. Okay. Here there's some kind of more information concerning diagrams that are made with full morphemes, but we skip this. Okay. And by this colimit construction, we can prove there's some work to do this, and it's not so simple. But the idea is to recognize the construction of the cumulative construction of SA or ST as direct colimit, in fact. So we can define by transfinite recursion a convenient family of diagrams defined on intervals of ordinals, or this means in successor ordinals, the category of the partial suralgebra, in fact, the small partial suralgebras. And we can depart from any small partial subalgebras, and the initial step is just choose these partial subalgebras, and we can do recursive construction of these diagrams, and the direct limit of direct colimit of these diagrams provides another pool or another proper class. So algebras, not only partial, but if suralgebras, they are proper class, as you have seen. And we can do this imposing construction that cyclic or transitive. And we have a canonical morphism, kind of inclusion of this initial step to this colimit. Is the arrow from the component to the colimit. And this satisfies a universal property. In fact, this universal property. Given any total suralgebra or transitive suralgebra, and a morphism from I to S, there is a unique suralgebra morphism that extends this morphism H. H tilde is this unique extension. And in particular, if we depart from the initial object of partial suralgebra, is the suralgebra that has the unique member that is star, that is T, MT, is star. So the previous defined SA is isomorphic to this construction, this direct construction. The previous defined ST is isomorphic canonically to this construction departing from the initial object. So, in particular, we have that SA is universal, if you prefer, initial object over all suralgebras, and ST is universal or initial over all transitive suralgebras. The construction cannot, cumulative construction cannot provide us sufficient mathematical tools to prove that. So it's easier to give more structure to the category of partial subalgebras, and we'll have a more general result that has a corollary these two results. Okay. So now we let's recall the diagram that we want to do. So we here we have on the right side suralgebras. Here we have ZF algebras. They are, I will talk about this. They are not only classes, but have a kind of natural structure. And here, these inclusions, we call that there is also a map from numbers, surreal numbers to ordinals, the birthday function. There's also a map from this V star, that our V star now is the class SA of the initial class of SA. In fact, V is the initial surreal algebra, initial ZF algebra, and V star, that is SA, is the initial surreal algebra. So there's a kind of parallel between this one and this one. And these horizontal connections, I like heteromorphisms, like a chimera morphism, because the head is a surreal algebra, and the tail, the head is a ZF algebra, and the tail is a surreal algebra. It's a kind of comparison of between objects in different categories, okay? So that's the idea. So we have to pass to this comparison between ZF algebras and surreal algebras. I will do this very quickly, I hope. So let's talk about a bit on ZF set theory, the usual set theory. We have an intuition that what should be a finite set in naive set theory, but in ZF set theory, the idea of finite is given a posteriori. It is given only after the definition of the best infinite set, the set of all numbers, the least inductive set. So in fact, we have by axiom of infinite a construction that is the set omega, and we define a set to be finite whenever there is a bijection between this set and the initial segment or a member of the set omega. Okay. So the idea we can do this analogy. We can say that the idea underlying algebraic set theory is to do the same thing, but not between finite and infinite, but between the notions of set theory. So in set theory, be a set or be a member or is a primitive notion. Now in algebraic set theory, it is not a primitive notion, but it's a derived notion. So let's see that. So the universal class, the class of all sets, set its parts is the class of all its subsets is large because they coincide with V, but is as by reunion, taking reunion, the operation of inclusion, reunion here, is a small complete lattice. So there's arbitrary reunions of sets, okay? And also V has not only this structure, but it has also a natural end function, this called this successor function that given in set V determines a singleton that's also a set. It's an end function. So in algebraic set theory, the main notion is the notion of ZF algebra, that is large, small, complete lattice, L is the suprema symbol, and this window also with kind of succession function is an end function. And for instance, V with the reunion and the singleton function is not a ZF algebra, but is the initial or free ZF algebra. And the ordinals with the reunion and the plus construction, the section function of ordinals, defines a ZF algebra that free among the suralgebras, the ZF algebras, where the subsector function is increasing or inflationary. So both can be defined a posteriori as or identified as by these universal properties. In this sense, we can define set or ordinal as a derived concept in this categorical approach to set theory, we call it algebraic set theory, given by Rangel and Commutative. And there is also derived set theory, the theory of the free model. So, as we can recognize the classical logic as the derived logic of the free Boolean algebra on omega generators. So in the same way, we can identify the set theory as the derived set theory of the pre-model, where the membership is defined by this relation that is now primitive. We have order given by the Suprema. We have an end function, and this, if we interpret this as singleton x is included in y, this means precisely that x is a member of y. Okay. And we have defined in both directions certain classes of suralgebras with extra structure, and also on special ZF algebras that this expansion will span this relation between ordinals and surreal numbers, and not only spans this, but explains in some sense the role of this relation. Okay. There's some technical definitions here that we pass very quickly. We have defined the notion of this, what is a epsilon ZF algebra, or a more general notion, standard ZF algebra. Of course, the class, the universe class and the class of ordinals provide these examples of these standard ZF algebras. In these standard ZF algebras, the derived relation epsilon is a well-founded relation. It's a part of the definition. And we can perform constructions like space of signs that is a way to define the surreal numbers through the ordinal numbers. The technical connection here between a surreal algebra and a class, a well-founded class. In fact, we think about the class as the underlying class of a standard ZF algebra. For instance, we think as examples here, C as V, the class of all sets, or C as on, the class of all ordinals. And this beta function here is that we call anchor, is a generalization of expansion of a proper expansion of the notion of birthday function the connection that connects surreal numbers and ordinal numbers. Okay, it's a very technical definition with 7 items, and I do not reproduce here. But there's our main examples that are the initial surreal algebra or the initial transitive surreal algebra or the surreal numbers are naturally anchored by some definition of these anchors. We can define through this anchor well-founded relation in this surreal algebra. We can define the notion of what is a hereditarily positive member of surreal algebra, though with such an anchor. And these hereditarily positive members, think about the ordinal numbers are the hereditarily positive surreal numbers, okay? And by this technical definition, we can recover this effect, and we can expand this using the anchor of the surreal, free surreal algebra onto the class of all sets. And we can also define a space of size. So, some certain conditions. Okay, it's a technical way to provide these connections between surreal algebras and ZF algebras. So we have now we have again this diagram that was our main goal, and I will explain now this again to summarize all we have talked about since then. So here is the connection between ZF algebra. This rank function is the unique ZF algebra morphism. The inclusion is not does not preserve the successor, so it's just the inclusion, but preserve the order. Here is a kind of inclusion and reduction. It's a heteromorphism, because in the left side you have ZF algebras, on the right side you have only sur algebras. So this B star is the anchor of the free surreal algebra onto free ZF algebra V. So see the analogy. This is an expansion of the connection between ordinals and surreal numbers, because some diagrams here commute, and R star is the unique morphism, surreal morphism from that one to surreal numbers, because SA is the initial object. So this is just, we have to just set. I just want to emphasize that the inclusion of this V onto SA is given by recursion in a very natural way, this way. So then X is a set, and the right side is a member of SA, and the anchor of SA onto V is given recursively in this way. You have to provide a proper well-founded relation to define this, but I will skip the details of this work. So almost all the diagrams commute that the previous slide. Almost all, unless this one, this arrow, this composite arrow, is less than this composite arrow, but not always is equal. Let's see. Okay. But all the other relations are identity, many retractions. So many commutative relations, but some there is just one of them just less than. This comparison is between the codomain that are functions from SA to the ordinal number. So this component-wise definition of order. So we can induce on SA well-founded relation by pushing this by B star. Okay, this press relation, this elementary symbol here is defined this way, and this is a well-founded relation. If U is less than V, then U is we call simple than V, or V is simple than U. Simple because U is born previously than V is born. Okay, this is the notion of birthday. Okay. And on the other hand, if X and Y are sets, and X belongs to Y, this occurs only if and only if the inclusion of this V for SA by J star, J star, is less than J star to apply to Y. So we almost there. We are going to provide this finally the definition of the set theory in SA, that is the free through algebra, as in algebraic set theory. V, the class of the all sets, is the free ZF algebra. We have some definitions to do. Given any subset here, we can define a new member of SA, positive definition, and a negative definition put on the here on the right side the empty set, or in the conversely on the left side the empty set for the negative part. This is a natural definition, and we have this relation. Okay. And finally, what we mean to be a set theory in SA? What are the desiderata? What are the requirements for a theory be a set theory for us to this talk? We select three. Okay. The first one, A, is that the theory or the structure have the potential to define arrows category as entities of the theory through binary relation. So the notion of function in set theory is a certain set that satisfies some definition. You have to define singletons and doubletons and order pairs and relations and functions a certain relation. So you have to impose that we have the same path to do this. This is one requirement. The other one, that's more algebraic one, let's say, that's the internal theory of the free object in this category. The internal theory is, to be more precise, the theory of the free object in this category. So we have already an object to analyze. We analyze the free object, this theory, in this category, and we put definitions on that. And the derived internal category given by item A should be topos-like. You have to be able to construct things like explanations and parts and products, and so these are kind of natural requirement from other side of category theory, other view of set theory, truth, category theory. To have a topos-like category, internal category. We have bijections that we just defined previously. Here, this map is a bijection between the small parts of SA to the positive members of SA. We have also a kind of stationality property given by the following. A member X of SA is determined because A is determined and B is determined by the members of SA that are smaller and simpler, or for B, the members Z that are simpler than X and such that X is smaller than Z. So we can recover the information in some sense by an extensional information. So we use this notation L of to mean the left part of a member. So this holds if only if the cut AB is in the left part of J star of Y, and this holds if and only if there is a unique member of Y that J star of X is the conic cut AB. Okay. So we have a kind of relation between languages. The language of ZF is given by the membership relation, and we have also these two relations on let's say two natural relations on surreal algebras, that the free surreal algebra SA that's given by the left member or B and a right member of a member. The positive language is given by this relation, this language only given by L on the right, the L minus is given by the right relation that is a combination of be a member, be a simpler, and be smaller, or be simpler and be greater. That's two binary relations simultaneously to consider. People like Paul Harlish that work on surreal numbers still have job, let's say, results on structures that are kind of surreal numbers, but endowed with two binary relations, the simplicity relation and this order relation. Okay, so it's a very natural also for free surreal algebra. And we have some left interpretation of the formulas of ZF to the formulas of surreal language. That to membership from variables, we associate the relation, and that's the obvious extension to complex formulas. And there is also a reversing relation, obvious reversing relation by putting this the other way around. This positive set theory extends the set theory in V. And we can define a set theory in SA that's compatible with the set theory in V through preservation of the notions by the maps J star that includes V to SA, and partially that's preserved also by the map, the birthday from function from SA to V. And this explains why we have a kind of new set theory ranked on surreal numbers like this. That stands the usual set theory given by V that's not really ranked on the ordinals by the rank function. There's a long list of definitions that will pass very quickly, so we can associate to. On the left side, we have sets. On the right side, we have a positive member of SA. So we have sets of SA, and we associate a member of SA in this way. We can define a singleton, the extension of notion of positive singleton, positive ordered pair, immediate successor and predecessor. We can define the inclusion relation between members of SA in this way. So every left member of one, the first pair is including the left member of the second pair, and the other way around for the right side. Okay. We can define the expansion of the notion of intersection, the reunion. We have the very natural properties of this inclusion relation, and for this reunion and intersection, they are supremely infinite for the inclusion, star inclusion. We can define what is the positive power set this way, and the relation between reunion and power set is preserved in the sense the same sense the relation that is, in fact, span the relation between a union power set in set theory. We can define relations, domain, couple of relations, domain, codomain, Cartesian products, diagonal, positive relation, proposition, function, injection, surjection, bijection, in very simple way using this left part. Okay, I do not go to read this for you. Cartesian product is a pair of, in fact, is a positive part, positive version of a set of pairs, okay, where A is in the left part of A, and so on. Composition is the natural one. And the mapping J star, we denote by J plus, preserves all these constructions, but not only this preserve like this, preserve singletons, but they reflect singletons. If the image of some member of some set Z is a positive singleton, that occurs that Z is a singleton, right? It's only one choice of singleton to preserve this. So it's not only preserved, it's a kind of elementary map, okay? Preserving reflects many constructions. And B star or means B restricted to the positive member of SA preserve many constructions, but not all. But the birthday function is good, but not so good as J plus. We can provide versions of axioms like extensionality or empty set or reunion or regularity, etc. And we can do this by or considering let's say full members, not only members of positive numbers, but for us that is more interesting for the moment is consider only stationary defined by the left parts, not simultaneously left part and right part. It's a kind of ternary relation, and this is a binary relation. And we can prove that these properties are holds in SA. It's not an axiom. Recall that SA is given previously, and we are analyzing the theory of a model. Like I said, the set theory is the theory of the free model V, the free ZF algebra. Here, the axioms this occurs also in algebraic set theory. They prove that the free ZF algebra satisfies an intuitionistic version of ZF axioms. And as I've said, there's positive versions of the many axioms, all axioms of the set theory, and we have a meta theorem that compares relations scheme indexed by formulas of ZF. This is one. When we transpose one language to another and transpose a set by its embedding in SA, some relation holds if only if the other relation holds. The satisfaction relation holds for V if only if this satisfaction holds. So we are in the almost done. I'm sorry by the long talk, very long talk. I hope that we are finishing by 5 or 5:30. For 5 minutes, we are done. So we have internal categories in V and SA. Since we can build positive sets of order pairs, we can define relations and functions that are positive by going as we go in the class of all sets. And this composition of functions and relations is associative, and this works very well. And we can define as a category, in fact, a corpus of given by the positive members of A. The object of this category is the positive members of A, and the arrows are the positive functions. Composition identity is analogous to the V case. And in fact, the function that maps V to SA, or in fact to positive members of SA, is stands to a functor. Be standard to a functor. So set is the category associated to V, the theory of V, and we denote by cat plus SA this category, and J plus now is not only a function but a functor, since J plus preserves functions, as we quickly passed a few slides ago. So we finishing the talk. Some remarks. The expansion that we have just done is one. This functor is okay, it's nice, this preserves and reflects many properties, but it's not a very interesting expansion. A much more relevant expansion that was not so clear how to perform this is will be, if someone try to do that, be more interesting if we consider not the left relation, not left property, but the ternary instance relation. On that means that y is determined by x and z, in the sense that y is between x and z, the less than relation, but y is and z and x are simpler than y. So it's a kind of relation that occurs in geometry, the between relation, between points. Can we do that? Can we define function and have a nice category and functor from between these two categories? This is the category of sets. And this category is in fact corpus. Nice question, natural question. And I skip this, but now I just have to mention that many analogous ideas, more or less analogous ideas, have appeared by the hands of Hankins, where he defined the notion called pedagogic D-graph. That's a set of a binary relation that is graded in the surreal numbers. But the emphasis there is not on this full structure. There is no full structure. There is no term function. There is no consideration of second order. But this pedagogic graph is very useful. This is a kind of price limit of some graphs, graded graphs, as the natural, the numbers, the surreal numbers are price limit of the class of all linear order sets. We call that Q the set of all rational numbers is the price limit of the all finite linear orders. But not the class of all surreal numbers is a proper class price limits of all linear ordered sets. This implies many interesting properties on the number of the surreal numbers. All the theoretic properties, the kind of universal linear order. But Hankins applied this to provide results, very nice results on ZF, the class of countable ZFC models. These are one main results in this paper. But we can ask ourselves if we can construct new models of ZF or ZFC by replacing these Hankins D-graph ranked or graded on surreal numbers by our category. So the question is more or less in the same direction, that forcing models or Boolean models of set theory can be encoded by the topos of sheaves of a complete Boolean algebra. So can we reproduce this idea, or more interesting, can we use the ideas of Hankins in this new setting? Can we produce new results on ZF, on the ZF theory, as models of ZF theory? And we can also consider naturally surreal set theory with good elements, since we can depart from a partial surreal algebra that's a set, maybe even a linear or the partial surreal algebra. We can construct these relative versions of SA and ST or natural numbers or surreal numbers. Can we perform an interesting theory of surreal set theory with good elements? I think is that. Sorry by the long delay.
Thank you very much, Hugo. So, is there any question, comments? As usual, please just manifestate first in the chat to avoid a lot of people talking at the same time.
Okay. I stop the presentation, okay?
Okay.
So it's a kind of technical more instruction, but I hope the motivations turn out to be more or less clear that what I intend to do. Some parts are, I should say that really technical to check that all the things we want to do really works, but I try to skip I do not able to skip the definitions, but I think I will be able to skip the technical details. I hope if you remember the diagram that we emphasized, this the main message of this topic.
Just a curiosity, have you any insights on the usage of sheaves that you present in the final remarks?
Sorry, please stop.
Do you already have any insights on the usage of sheaves to show the extensions?
Sheaves?
Yes.
No, I do not try to do that. It's a very natural question, let me say, because since we talk about should be a topos like category, natural question will be it's a rotating topos, for instance. I'm not trying to do that, but it's a good question.
Thank you.
I don't see any clear candidates of site or, but I will think about it.
Hugo, Petrúcio here.
Oh, wait.
I have a question, a silly question maybe, but
not at all.
You mentioned that you are trying to build ZF set theories. Okay?
My microphone is very bad. Can you speak very?
You mentioned it. You are building Zermelo-Frankel set theories. What happens with the other set theories?
You mean NBG? Or
for example,
it's a good question because I put this idea of ZF algebra. ZF algebra, we have a naive approach to algebraic set theory because algebraic set theory is a very categorical technical device that presupposes a topos, and in this topos we consider a class of maps or the small maps that are closed by many constructions, and then it is defining this ambient topos, the idea of ZF algebra, and so in fact we can ask ourselves if we can really do all of this inside topos. So in certain sense, what we have done is just a very naive way to construct this in the tops of all sets, or in the topos of all classes. We have to pass to a bigger universe because ZF algebra is a object of this topos. So the idea that we have is not the tops of all sets, but the topos of all classes. So I think there's There's some, I think there's many technical conditions to perform this in more or less general topics, because we do not need choices in some constructions, but we do need middle excluded and so on. So I don't see how this is mostly to all general algebraic set theory, but maybe in some topics this can be done. I think this as a background topics for an algebraic set theory. There is some kind of possibility to consider other set theories and other surreal set theories.
Okay.
Any other question?
I have another one, if
Sure.
yeah. I think it is related to the first.
Yes.
You mentioned that you are imposing some tutor to be topos-like.
Yes, yes.
What does it mean exactly? I mean, it's not supposed to be a topos, or it is?
Just kind of like a requirement, like desiderata. We try to not to be so precise, because we have to check if what we in fact have performed after the construction have done. But the idea of topos like it, that we have some kind of space of functions like exponentials, and we have some part function, part of objects, but not a categorical part or classifying of objects a priori, but we can in fact prove that these constructions cat plus SA is equivalent to set. That is not a nice result. This is why unless I have done some mistake in some part, but there's this canonical functor has a retraction, and it's more than this. That there is a two natural isomorphism between the composed the identities. So there's an equivalence of category. So in fact, this is a topos, but the silly topos, the topos of sets. And what is meaningful, it's if we can do this for a expansion topos that spans the tops of all sets. And it's not so simple to construct this. What's the nice candidate to define this? It's a kind of frustrating, I have to say. After work a lot, we just find the topos of all sets.
Okay, thank you.
Any other question? Okay, so thank you very much again, Hugo. And thank you very much, everybody who watched.
Thank you for the invitation. To me, it was a pleasure to talk about this.